Okay, now it'd be really easy to redo this and pretend I never made the really embarrassing mistake I did. But obviously, I'm integrating when I'm differentiating. And I looked at it 2 or 3 times. Well, the integral of e to the negative s dt is negative 1 over s e to the negative st. Except I'm taking the derivative of that, which is obviously this. So that 1 over s was really bothering me. I knew it couldn't be, I knew it had to be s. But I kept looking back here and trying to integrate that. I don't know why. Okay, so there we have it. Okay, and now we derive the Laplace transform for f prime of t using the same steps, practically identical steps. And we found that that was, okay, we've already got our minus f prime of 0 here. That was right, that worked. Although I tried to put an extra negative on that, if you remember. Apparently negative signs are the first thing to go. That's then going to be s times the Laplace transform of f of t minus s times f of 0. And now if we multiply this out, we get this. And it's, I'm distributing before I finish writing the thing down. If I distribute through this, I get this. Okay, so that this works out, and this is now an expression that's not difficult to understand. Okay, we always have our Laplace transform of f of t, and no matter what Laplace transform we're taking, no matter how many derivatives we're taking, we're going to ultimately be, when we do the integration by parts, we're going to get an integral that has one less prime on it, like we did here. If we started with a triple prime, well, we'd be doing f double prime of t prime. Okay, and we'd have an f double prime of t in here, and we get an f double prime of t here, and then we do another integration, and we get, we'd be doing the f double prime integration, and you can work through the details of how that works. You're not going to understand it very well from my mumbling here about it. You see that ultimately you're going to get down to an integral of e to the negative st times f prime of t, and that's going to be your Laplace transform of f. Every time you do this, you get another negative s here, and of course when you do that integral, it's going to become a positive s, so that you're going to end up with, if you tried the third derivative, you would have an x cubed times the Laplace transform. You would have done 2 integrations by parts before you got to this, and each one would have given you an s. So you're going to have s to whatever number of derivatives you have here. Okay, and you're going to then have 1 less s times f of 0. Okay, because of this factorization here. And then every derivative you take, with your f prime of 0, you're going to have 1 less s on it. And of course, you don't have any here. If you had higher derivative, you'd have an s to the n times the Laplace transform of f of t minus s to the n minus 1 times 1 times your function value at 0, and then minus an s, 1 less power, times your f prime of 0, and so forth, until you finally get down to your nth derivative of f at 0. Now, I'm waving my hands and saying that, and you could have quit this video a long time ago if you're not understanding what I'm saying, but that explains, briefly at least, the formula that you see for the Laplace transform of the nth derivative of t. And by what I said, that's going to be s to the n times the Laplace transform of f of t plus s to the n minus 1 times f of 0 plus s to the n minus 2 times f prime of 0. And you keep going until you get down to the nth derivative of f at 0. And you're just going to have, you'd have s to the 0 here. Of course, s to the 0 is 1, so you don't even have to write it. That's the meaning of Laplace transform for higher derivatives. Now, everything we do here, since we're just doing a brief introduction, is probably not going to exceed the second derivative. But everything we do could easily be done with higher derivatives, and this formula would be useful.